Mass is nothing but energy, or in other terms, mass is another form of energy. Einstein showed from his theory of special relativity that it is necessary to treat mass as another form of energy, and he also gave this equation as energy which is associated to mass m is nothing but mc square, or mass m is nothing but equivalent to energy E, which is given by mc square. Of course, c is the speed of light, that is 3 into 10 power 8 meters per second approximately. Now, say what will be the energy equivalent to 1 gram of substance? According to this formula, 1 gram is 10 power minus 3 kg, and 3 into 10 power 8 is C, right? So its square will be 9 to 10 power 16. So you observe that it is very, very large. So if 1 gram is equivalent to such a large energy, what will be the energy that is associated to say a handful of substance, that is maybe a kg or something? It will be very, very large, right? Yes, that is why the energy released in nuclear reactions is very, very high. Just note that. Now, why am I telling this now? Because you know that law of conservation of energy states that the initial energy is equal to the final energy across any reaction, right? Now, you just take note of this, that energy associated with mass, this one, should also be taken into consideration for say the next few sections that we are going to deal with. Now, consider this atom 1608, that is an oxygen atom which has 8 protons, 8 electrons as well as 8 neutrons, right? Now, mass of 8 neutrons, what will it be? 8 into what is mass of neutron? 1.00866 atomic mass units. And mass of 8 protons, what will it be? 8 into 1.00727, that is the mass of proton, atomic mass units. And similarly 8 electrons, 8 into mass of electron is 0.00055 atomic mass units, right? Adding these three numbers will give me the entire mass of that atom, right? But adding only the first two numbers, that is mass of neutrons as well as protons, that will give me the mass of nucleus, right? Nucleus of that 1608, and that will be equal to 16.12744 atomic mass units. This is the expected value of the nucleus, right? Now, if we calculate the mass of this nucleus using mass spectroscopy, the mass of atom was found to be 15.99493 atomic mass units. Well, okay, this is the mass of atom that is found using mass spectroscopy. So let us subtract the mass of electrons from it, which is 8 into 0.00055, right? Atomic mass units. So finally, I'm going to get it as 15.99053. This is the observed mass, that is mass found through the experiments, right? But actually we expected it to be something like this, right? 16.12744. So the observed mass is less than the expected mass, and it is less by 0.13691. Just subtract those two numbers by this much amount. This is known as mass defect. So the mass defect delta m is given by the mass of protons, that is atomic number into mass of one proton, plus mass of neutrons, that is total number of neutrons into mass of each neutron, minus, this is the expected, right, expected mass, minus the observed experimental mass. So this is how you calculate mass defect. Well, why am I interested in this? Because my mass is found to be less. Why is it less? Because if you bring certain neutrons and protons which are far away initially, and when you bring them close, they form a nucleus, say some with some neutrons and with some protons. In this process of formation of nucleus, some energy is released. That is the key point. That energy is known as binding energy of the nucleus, and that energy, that binding energy, will be exactly equal to this mass defect times c square. That is that binding energy is nothing but the equivalent energy that is associated with this mass defect. So that mass defect is manifested as the binding energy between these nucleons. That is how you have to read it or get intuition for it. Now, other way of saying it will be these are bound together inside the nucleus, right? So I'll have to provide a energy EB, that is this much amount of binding energy. I'll have to provide it externally to separate these nucleons again. Got it? See, nuclear binding energy is nothing but the measure of how well the nucleus is held together. So, more the mass defect, more will be the binding energy, and hence you can say that more closely or more tightly are the nucleons held. So now you know what is binding energy, right? There is something called as binding energy per nucleon. It is obvious from the name itself. It is nothing but EB by A. That will be the binding energy per nucleon, which is represented by Bn, EBn. Okay. So just divide the binding energy by the mass number, that is total number of nucleons. You will get the binding energy per nucleon. This is the graph. If this is the mass number, this is how it varies. You have a maximum here for somewhere Fe56, right? And here the value maximum is 8.75 million electron volts. And for 238, when A is 238, you have it as 7.6 million electron volts. And you see that when this is some area which is of interest, because you see that in this area this nuclear binding energy per nucleon, that is pretty much constant, right? Well, it is varying but not much. So this is our area of interest. When you take atoms with greater mass number in this region, then the value is going to be less than this, as well as in this region it is also going to be less than this, but here it is varying but pretty much constant. That is of interest to us. Actually, that region can be roughly set as greater than 30 and less than 170. That is our area of interest. This is mass number. Okay. Now, why is it not changing there much? Let me give you the explanation. See, the binding energy per nucleon is influenced by how many nucleons are surrounded or surrounding that particular nucleon. So you have nucleon here. It has something called as short range force. Short range nuclear force is one of the four basic kinds of forces, and it has a very short range. And if any other nucleon is present in that range, then okay, they'll show effect on this. But when you have some decently large amount of nucleons, and say if you add one more nucleon to this cluster or to this club of nucleons, this added nucleon is not going to show any effect on the nucleon which is present inside or which is far from it, because it is not in the range. Are you getting me? This applies for every nucleon. So when you start with one nucleon and slowly when you add nucleons, initially since it will be in the range, so initially there should be some dramatical change. That is why you have graph which is very much changing in the beginning, and slowly when your number of nucleons is some 30 or 35, then you will see that the added nucleons are not showing much effect on the inside nucleons. Well, they are affecting only those nucleons which are in their range. Hence the binding energy per nucleon is changing. Observe that here also it is changing, but not much. This property that a given nucleon influences only those nucleons which are close to it, it is known as saturation property of nuclear force. Now, why am I interested in this area? This area is of interest to me because the nuclei which are in this region are having more binding energy, and so I can say that the nuclei which are present here or in this region, they have less binding energy per nucleon. So if I am able to convert these nucleons and these nuclei into these nuclei which are having more binding energy per nucleon, then it is something like creating energy. Or because you know that when stable nuclei are formed, energy is released, because when we brought a proton and neutron together, we saw that a nucleus forms and energy is released, right? It is something similar to it. Let me give an example. Say if you have an element with mass number 240, say an element with 240 mass number belongs to this region somewhere more than 170, right? If I am able to convert that into, say, two elements of mass number 120 each, and mass number 120 belongs to this region which we are interested in, that is that region which has more binding energy per nucleon, and hence here the nucleus or the nucleons are more tightly bound, and hence my energy is released in this particular process. And this is of very much interest to me because energy is released in it. This process is known as fission, where a nucleus of higher mass number is splitted into nuclei of smaller mass number. And the same thing can happen, that is, energy release can happen if nuclei belonging to this region, the less than 30 region, if they are getting converted to a nucleus of this region, then also energy is released, because finally our aim is to increase the binding energy per nucleon so that energy is released. And if it happens this way, that is from here to here, that is known as fusion. Of course, we are going to discuss about this fusion and fission in detail in probably the next video. Just get the initial idea now. Inside a nucleus, there are nucleons. Some of them are neutrons and some of them are protons. But when they are very close, why are these protons not getting repelled and thrown away far? Because there is some other force which is attracting them. Actually, there are four types of forces in the entire universe. Weakest of all of them is gravitational force, and next is weak nuclear force, and above them you have electromagnetic force, that is due to electricity and magnetism, and strongest of all the four is nuclear force. And the nuclear force which we are talking about now, it is a very short ranged force. You see this graph, it gives the nature of that force. So note that this is 10 power minus 15, that is femtometer, very small. So if you are, say, 3 femtometers far from your nucleon, then pretty much it is zero. It is not influencing the other nucleon. It is maximum, that is attractive forces, when it is negative, right? We have a maximum here. It is maximum when the distance is around 0.8 femtometers, and here it is 0.5. So when it is 0.5 femtometer, it is 0, and if it is closer than that, it is going to be repulsive. Okay, this nuclear force is very strong. It dominates all the other types of forces, and that's why it dominates the proton-proton repulsion also, and hence you have all the nucleons bound together inside the nucleus. And note that the nuclear force doesn't depend on charge. In other words, I can say that the nuclear force between neutron and proton, as well as proton and proton, as well as neutron and neutron, all are the same. So observe that when you are, say, 2 or 3 femtometers away, or the distance between the nucleons is 2 or 3 femtometers away, then the nuclear force can be neglected, and that is why you have something called as saturation, which we saw just now. That is, we saw that in large nuclei, the binding force per nucleon was pretty much constant over some range. That is because of this property only, that the range of this force is very small. If it was very large, then all the added nucleons would have shown effect, right? So it wouldn't have been that way. So this leads to saturation of forces inside a medium or nucleus. That's it for now. Keep watching. In the next video, we'll start radioactivity. Don't miss it. It's going to be interesting. Bye.